Okay, morning. Welcome to our colloquium for today. It's my pleasure to introduce to you Professor Zhu Han. Zhu obtained his PhD at the University of Maryland in 2002 and spent a few years there as a research associate. He joined Boise State as an assistant professor thereafter, and found the Northwest only to his liking for a couple of years. Since Boise, he fled down south, and he's at the University of Houston for several years now. He spends a lot of his summer, I noticed, at most interesting places ranging from Princeton and Stanford to Korea and Norway. I see Seattle is not on his list, but I expect it will be at some point of time.
I'll be here soon.
Zhu's work spans a significant range of current interests in terms of topics such as compressive sensing, as well as applications to emerging areas like smart grid. Today he'll be looking at his talk will be looking at applying notions of compressive sensing to another hot area, notably that of cognitive radio. And he's going to specifically from his talk look at applying notions of collaboration and compressive sensing to this problem. So let's welcome Zhu. Thank you.
Okay. Thank you very much for the introduction, and thank you very much for the invitation. And today it's my great pleasure to be here. And I will talk about the compressive sensing and its application into the different areas, such like the cognitive radio and some other area, like the Lidar or some other applications. And this work is supported by NSF, this grant. Okay, here is the outline. First, I will talk about the basic for the compressive sensing. And then I will discuss the application, like this collaborative spectrum sensing and multi-spectrum LiDAR. I will spend more time on these two topics. Then I will briefly discuss what is the, how can I say, other work that I have seen in the literature. And finally, I will talk about some of my other work. And here is the part one. We want to talk about compressive sensing. What is the motivation and what is the basic concept? And for the traditional system, okay, usually you try to sample at a very high speed. For example, you buy a digital camera, and which have a super high, CCD number of megapixels. And then right after it gets sampled, it will do the JPEG compression. And then you compress it very hard. And then the question is that, okay, this kind of CCD will cost you, the high resolution this CCD or high speed ADC will cost you a lot of, its cost is very high. Then the question is that could we reduce the speed of this kind of, the number of pixels for this one, will still achieve the same kind of performance. Because right after sampling, you do compression. How about we compress early, before the sampling? Then this is a kind of motivation for the compressive sensing. And for the compressive sensing, we try to, compress and sensing, put them together, combine together. And then this is what we want to talk about. So what is the compressive sensing? We have a vector x, which is huge, with dimension of n. And among this, n position, there are only k non-zero component. And this k is much smaller than n. K is much smaller. And this is called sparsity. This is sparse. And this can be sparse in the different domain of each. And it's not sparse in this kind of domain. When you do CCT change, in frequency domain, it's very sparse. This S can be sparse in any domain. For just say, most of the are zero, some few zero components. To know where is zero component, sample at which is very high. So the question is that we reduce the sampling rate from n to some much smaller value, well, we still can reconstruct where is a non-zero component. So the compressive sensing means, okay, I have this vector, then I multiply matrix, random projection matrix, means phi. And this phi have the dimension of m times n, where m is much less than n, much less than n. And then I can have a new measurement y, which is a dimension of m times 1. And then I try to sample this y instead. And we can see that, okay, m is much less than this n. And when we sample this y, after I sample this y, can I reconstruct the original x with some kind of high fidelity? And the answer is yes. Okay. In the literature, they show that, okay, as long as m is greater than k log n divided by k, we can reconstruct this x from this y. And because k is a small number, even though n is a large number, but log n is a small number, so m is still a small number. We can see that, okay, then, okay, we can see that, okay, we reduce the sampling, from this n to m. And after that, we can reconstruct this kind of original signal by some kind of algorithm. And here is the example. Suppose I have for example, this is 300. Suppose let's say, okay, this is 300 channel, for example, okay? And then there are only 4 channels that have some kind of value there. And you don't know where it is for. And according to the Nyquist theorem, you have to sample at a very high speed rate. But, this is x. But then what we do is that, okay, we do some kind of random projection with a phi. So the dimension is changed from 300 to 25. So there's a random projection here, such that, okay, it's reconstructed into this y. And this y is nothing related, does not look like the original signal. However, by using this kind of linear L1 minimization, by solving this one, we can reconstruct the original x with a high probability of success rate. So we can see that, okay, by using this compressive sensing, instead of sampling at the rate of 300, we can sampling at the rate of 25. And let's go back a little bit. I forgot to mention that, okay, this phi, for each component of this phi, is a random variable. And this phi can be, for example, by random Gaussian, or +1 or -1 with a random variable. So this phi, okay, is a, how can I say it? It's a known matrix, but each component is enough. So by using this one, okay, we reconstruct. So this is an example for that. And for the compressive sensing, okay, it's an emerging field for the research for signal processing. I went to the ICAS last year, and I found out 40% of the paper about compressive sensing. It's a really, really hot topic. And as the previous example showed that, okay, Sparsity beats the Nyquist theorem, 300 sample rate. Then the basic idea is sparse and then construct the original, and offers to original signal with a very high fidelity. This is about the basic sensing. Is there any about the basic background for the compressive sensing? And if not, okay, let's see, okay. The serial and the algorithm of sensing have a lot, but the key question now is that, okay, how to apply for the sensing. And it's a wide open area. And the key challenge here is that, let's go back a little. The key challenge here, okay, you sample for this y, and the random projection, in the domain, because you sample at here. So this random projection should be implemented before. And how can you do this random projection in your application? And it's a key challenge for that. And in this talk, we give some kind of example on how to implement this. So in the second part of the talk, first I will talk about this kind of collaborative spectrum sensing for cognitive radio. And this one is published in JSAC, and this is basically our NSF proposal. And for cognitive, here is the outline for this part. First, we talk about cognitive radio and collaborative spectrum sensing. And then we show our proposed system model and show how could we use the compressed sensing for this collaborative spectral sensing in the cognitive radio. And then we started two types of algorithms, the joint sparsity algorithm and the matrix completion algorithm, which fits into the different scenarios. And we have the simulation and the comparison for that. So for the cognitive radio, it's based on the observation that, okay, most licensed spectrum is unused by the prime user. And well, for some kind of public spectrum, like this ISM band, everybody just use it. It's very crowded. So the question is that, okay, if the prime user does not use the spectrum, could the cognitive radio use this spectrum? This is the motivation of the cognitive radio. I think most of you know this concept. Second user, in order to achieve the cognitive radio network, second user have to detect the spectrum hole, which is unoccupied by the prime user. So the detection is, spectrum sensing is very important. And the cognitive radio can improve the spectrum utilization, but the key enabler is the spectrum sensing. The cognitive radio have to know that, okay, where is this spectrum hole left by the prime user? So, however, when we try to implement this one using the SRP tool, we found some kind of challenge. The first one is that, okay, for the spectrum sensing, it's time consuming. It takes some time for this PLL or energy detector to detect it. So at each time, one cognitive radio will sense, for one channel. And there are maybe some other channel is still vacant. So in order to know all this kind of, in order to know all the spectrum over the different wideband, the cognitive radio have to kind of screen all the channel. And this one will cost time and maybe minutes. And this one will be a kind of, challenge for that, because after you screen the channel may be changed. So you want to see the whole spectrum simultaneously, then there will be a challenge for that. So this is the first type of problem. And the second type of problem is that, okay, for individual cognitive radio, you may in the position that the channel is faded. So you think the prime user is not there, then you try to transmit. However, this will cause this interference to the prime user if the prime user indeed exists there. So this is called hidden terminal problem. And in order to overcome this problem, they use a collaborative spectrum sensing, CSS. And for the collaborative spectrum sensing, multiple users try to observe the prime user and then send the report to some kind of fusion center. And then the fusion center determine whether or not the prime user is there or not. And by using the collaborative spectrum sensing, it's very unlikely that, okay, the prime user signal is faded for all the cognitive radio. So by doing this, okay, we can increase the detection probability. However, for this kind of collaborative spectrum sensing, multiple cognitive radios still see the same spectrum. And for the wide spectrum, they have to screen as well. So collaborative spectrum sensing does not solve the first problem. And in addition, the collaborative spectrum sensing also causes additional problem. For the distributed, for this kind of cognitive radio, they need to send a report to the fusion center. And because of channel fading, this report can get lost. And then have some kind of missing or error in this kind of, in fusion center. And then how could we this problem? So you can see that, okay, spectrum sensing, you have the challenge. Basically, for wideband, how could you sense it? And also, spectrum sensing, okay, how can you deal with the incomplete sensing information? So this is collaborative spectrum sensing for the cognitive radio. And what we propose is that, okay, instead of sensing the spectrum together, individually, how about we have some kind of filter bank or this kind of this kind of frequency selective filter, so that, okay, all the channel pass through this frequency select filter, and then they blend together, and then we sample this blended data, And then we try to use the compressed sensing idea to reconstruct the original signal. So by doing this, because we sense the whole spectrum simultaneously, even though they are mixed together, but we can save the time for that. And we can use the algorithm to recover the original signal together. So how could we, formulate this problem? And suppose I have a diagonal matrix, R, which has the n by n times n dimension, where n is the number of channels, which is large. And this diagonal matrix have 1 and 0 on the diagonal. 1 means the prime user is there. 0 means prime user is not there. And you don't know where it is, but this R is sparse. There are only few components on this diagonal. So this is a matrix, and this is a channel indication matrix. And the second matrix is G matrix. G matrix is a channel gain matrix. That means from the prime user to the quantity radio channel, to the quantity radio. This is a channel matrix. But this channel matrix, I put it here in our algorithm. We don't need to estimate it. So there's no need to estimate this G matrix. And after the prime user transmitted to the quantity radio, we put into, for each quantity radio, we have a P, filter set. And this P filter set basically combine this N spectrum, N channel together. So totally I have each set have the, frequency select filter. So this F represents the response for this kind of frequency select filter. And for this filter, because those filter is that this matrix. After that, we have this kind of measurement. And this measurement needs to send to the fusion center. Send to the fusion center. And this mixing. And I don't the compressive sensing. So propose the sparsity. Here, this we as matrix, and R matrix is a diagnosis of only with some kind of non-component. So when they time together, for this X matrix, there are only kind of few rows which is non-zero. For the rest is 0. And then if we take any kind of a column in this X matrix, we time this F matrix, it's become any column, this M matrix. So this is one set of the equation for compressed sensing. Because this is a random projection, this is a sparse signal, and then this is measurement. And then here I have a set of them. So all this, I have a set of equation for this compressed sensing. All of they are so it's kind of sparsity, and all these equations try to influence each other, so that get this more solution. For sparsity, we try to, solve a compression them, then we can get this kind of for that. This is in draw sparsity. However, for the draw sparsity from result, okay, the draw sparsity, okay, when the sparsity, the sparsity must be can I say that must be low, or in other words, the R matrix must be very low rank. In this case, it will work. And on the other, and also, okay, the missing component in this M cannot be too large. Otherwise, joint sparsity will not work. So in other words, okay, for joint sparsity, first, okay, the channel, the spectrum sparsity level should not be high, and then, okay, the channel from this cognitive radio to the fusion center cannot be too bad. So this is a limitation for that. And then, okay, in order to overcome this kind of problem, we proposed another algorithm, which is called matrix completion. And the question is that, okay, could we recover the loss of the information first and then do the optimization? So this is called matrix completion. And for the matrix completion, you can see it as the matrix version of the compressed sensing. Basically, the matrix completion means I have a low rank matrix, and randomly I select some kind of component from this low rank matrix. And can we reconstruct the original matrix? So this is kind of matrix completion. And for matrix completion, okay, here we have this problem formulation. This is M equal to the frequency selective filter, channel gain, occupation indication matrix, and this channel gain. And then this M matrix, well, when it's transmitted to the fusion center, some component gets lost. So I have this ME matrix. So for the matrix completion, if I go back to this to here, and this M matrix must be low rank, because the highest rank that you have is this R matrix. So this R matrix, I have only K component there. So this M matrix must be low rank. And then I miss a lot of component. So I only have some kind of few component, which is transmitted. So with this kind of incomplete measurement, and in order to reconstruct the original M from this kind of incomplete matrix M, we use this kind of matrix completion and compare with the compressed sensing. Instead of using the L1 norm, they use this nuclear norm. And usually this nuclear norm plus some kind of L2 norm, which is a noisy denoise part. So this is kind of mean square error. And so this is this is a nuclear norm plus some kind of error term. So this kind of optimization is usually called lasso. And by using this type of algorithm, we can reconstruct the original M from this lossy M. And then we can do the eigenvalue decomposition. And whenever there's non-zero component, we know the prime user is there. However, think about this one. Okay, first, we need to do this kind of nuclear norm optimization. Second, we need to do the kind of eigenvalue decomposition. This will have a high complexity, because doing the eigenvalue decomposition is very high complexity. So for this kind of algorithm, it cannot fit into the network with a large, when this R is huge, when this N is huge, it will not fit there because of complexity. So there's a trade-off between these two algorithms. And here, we set up some simulation, and because the two algorithms fit into the different scenario, we have the two sets of simulation. For joint sparsity, and we have the large number of channels, 500 channels, and then we have 20 cognitive radio, and the number of occupied channels from 1 to 15. Well, for this kind of matrix completion, we cannot handle this large number of channels because of complexity. So we have 35 channels, and then we have the number of the occupied channel prime user is 1 to 4. And here is some simulation result compared with the signal to noise ratio with the missing detection and the false alarm. And also, I mean, this is for the drawn sparsity, we show the different performance. We can see that, okay, this kind of a missing probability is relatively low when in a reasonable signal to noise ratio direction. And also, for this, matrix completion, we also show the similar performance. And here we show this kind of sampling rate. I mean, this sampling rate is how many percentage of the sampling rate compared with the traditional method. And we can see that, okay, we can have 20% to maybe 30% of the rate, I mean, compared with the traditional method. So we can see that, okay, compared with this, by using the compressive sensing, and we can achieve, I mean, reasonable performance, and well, I mean, with much lower sampling rate. So compared with the two algorithms, for the drawn sparsity, it fits for the large network, but relatively small, I mean, there's a small number of prime users. Well, for the matrix completion, it fits into the small network, but it can have a relatively large number of prime users there. And well, how about this? If we have a large-scale network, maybe we can think about this hybrid method. We can try to mix these two algorithms together and then try to solve the solution. So basically, this is kind of compressive sensing. And for this compressive sensing for quantity radio, for collaborative spectrum sensing, the key idea is that, okay, how can you mix the prime user's information together so that you can use the compressive sensing. And the second thing is that whenever you get this data, how can you reconstruct it? And here we propose two algorithms, drawn sparsity and the matrix completion. So this is about the quantity radio. And then I will briefly talk about the other type of application. The first one is a multi-spectrum LiDAR. And for University of Houston, we have tons of this kind of funded research for this kind of LiDAR. And then this is a background, and they have the different equipment. They also have a plane for this one. So what is a LiDAR for? And LiDAR is can see through this kind of trees. And this is one image from this New Mexico. And then by using LiDAR, they can see through the trees and see the ground structure. And by doing this, you can have much more information. For example, in Maya, in Mexico, they use a LiDAR to find this kind of Maya temple, because Maya temple is usually under the tree. So by regular visible light, you cannot see it. By using LiDAR, you can see the different structure. And also, okay, they try to, in Egypt, they try to use the LiDAR to find the old riverbed of Nile. And then along the riverbed, they found the old pyramid. Anyway, there are many other different applications. So why we can use this kind of LiDAR, compressive sensing in LiDAR? The plane shoots the laser into the ground, and there are some kind of reflection on the top of the tree, or on small tree, or on the ground, or even underwater. So you will have some kind of response back to the sensor, to the plane. But where is this? You only have few. But where is this response? You have no idea, because it's you don't know the distance. So this is where the sparsity comes from. You only have very few components, but you don't know where is it. And why we need compressive sensing? Think about this one. This is the speed of light. And in order to get accuracy of 1 meter, and your ADC speed should 3 to the power of 8, because of light speed. So here you need a huge, very quick ADC. So the question is that, okay, could we reduce, this ADC will achieve the high resolution. So this LiDAR system, this is basically the LiDAR system. And in addition to that, okay, for different waveform, for the different material, they will have the different response curve. So in the multi-spectrum LiDAR system, you will have X, Y, plus waveform. You have a 3D data. And this 3D data is a lot of data. And then, okay, the question is that, okay, how could we reduce the sampling rate so that, okay, we still can achieve the same accuracy? So in order to do that, okay, we try to propose some kind of, 3D LiDAR system, and we use some kind of prism or this mask, try to mix them together. And then in this kind of after mix them in this kind of frequency and spatial domain, in time domain, we use this kind of compressive sensing, pseudo-toll together, and then we further mix together. And after that, okay, we try to see the result. And here is a simulated result. It's not the real system. Okay, from the simulated result, we can say that okay, when we reduce sampling rate to 10%, we can still reconstruct the order signal with a high fidelity. In other words, okay, we can reduce this kind of ADC speed by 10 times for that by using this kind of compressive sensing method. And so this basically thing, okay, in the how can I say that? With the light, with the laser part, we try to mix it together, and in this kind of signal, we also want to mix them together. So after that, we can reconstruct the signal. So this is how we try to do in this kind of LiDAR system. And beyond this, beyond the LiDAR, we have some other problem, other type of application. And for example, for OFDM is orthogonal frequency division multiplexing, which have the high data rate transmission, and it has the high bandwidth efficiency, and it works in your Wi-Fi or LTE system, 4G system. And the main challenge for this OFDM is this kind of channel estimation. And we try to estimate this channel. And for the OFDM channel, it can be represented like this. And this is a channel response, and this is a multipass component, and this is a multipass delay. And there are only few components for the multipass component, but the delay point, you have no idea where it is. So in order to estimate the delay and this response, and we propose a compressive sensing one. And here, the sparsity comes from this multipass component, only very few components, but you don't know where it is. And we try to use this kind of compressive sensing one. The basic idea is try to increase the DAC speed in the transmitter while keep the same ADC as a receiver, so that we can achieve this kind of mixture effect. And after that, we try to test on this kind of AO211A system. And then we show the mean square error with a different signal to noise ratio. As a matter of fact, I should plot this Kramer law bound in this one as well. So we can show that, okay, the proposed compressive sensing is achieving some kind of a near optimal solution, for this kind of channel estimation. So this is OFDM. And this is, another application is this MIMO system. And for MIMO system, here you have this time of arrival. Here you have the different antenna. For this electrical wave in the high frequency, it looks like the tsunami. It's moved to the wall and then bounce back, something like that. So for the different antenna, they will receive this kind of electric wave over the different time. And they are highly correlated to each other because the time of arrival is have some kind of pattern. And by exploring this pattern, we can use this kind of joint sparsity and for this kind of compressive sensing solution. And this is another type of this MIMO system. And the next solution is this localization. And suppose, okay, in the network, this let's say, okay, prime user may be located into the different location, and we only have few prime users there. And the possible location is very few. So possible location is a lot of possible location. So this is where the sparsity comes from. You only have few, prime user, and it can be anywhere. So the question is that, okay, could we use a compressive sensing algorithm so that we can try to locate these users? And there are some kind of recent work by Giannatis, and last year in signal processing, transaction signal processing, try to use a compressive sensing method for this type of, localization. And we also try to implement this one using some kind of USRP2 and for this localization. And another example is that, okay, because I came from Houston, Houston is a oil company. There are so many oil companies. It's the capital of the oil industry. And what they want is that, okay, they want to see the underground. What is the structure for this? They want to see whether or not there's oil there. So what they will do is that, okay, they have the explosion, and then send the wave down, and then they put the sensor on top of the ground. They try to get this information. However, there are two problems. First, some part of the ground you cannot put sensor on it. For example, around the residential area, or there are some lake or river or mountain, you cannot put the sensor there. And the second thing is that, okay, deploying sensor is very expensive. It costs millions of dollars per day. So the question is that, okay, some part I cannot deploy the sensor, so I have missing component. And the second thing is that, okay, I want to reduce the number of sensors so that I can, reduce the cost a lot. So could we use the compressive sensing for that? And yes, instead of have one explosion, we have the multiple explosions together so that the signal will mix together. And then the multiple explosion will send the signal, but when it comes back, well, the signal will mix together. But this mixture will provide the opportunity for the compressive sensing. And here is some simulation result. This is a traditional method use MMSE solution. This is underground structure, and we got a signal-to-noise ratio of 8.9 dB. And by using the proposed solution, proposed compressive sensing solution, we reduced the sampling point by 50%, while the signal-to-noise ratio increased to 16.1 dB. So we can see that, okay, by using the compressive sensing, okay, we increase the signal-to-noise ratio while reduce the number of sampling. And my first PhD student graduated for last year for this compressive sensing in cognitive radio, and after she graduated, she founded our company for this. Yeah, she works now for our company for this. So by using the very similar idea, we can try to find this kind of concrete flaw detection. Sometimes the bridge have some crack into it, so how could we detect it? And then basically, okay, we can put some kind of piezo, to send the wave into the concrete. And the wave will have some kind of response, and then there are some sensors there. So you can detect some kind of cracks there. And because it's very difficult to put the sensor into the concrete, and also the location you can put the sensors are very limited. So then you need some kind of the accuracy cannot be high. So we can use a similar idea of compressive sensing, and then we put there together. So by doing this, okay, and we can, how can I say that? By using the compressive sensing, we try to detect this crack. So very similar to our company example. And finally, okay, as you know that, okay, we have this BP oil leakage, and when you go to the Houston now, do not eat the seafood because it's dangerous, and there are a lot of oil here, okay. And then, okay, by here, because oil can be anywhere, and in order to get this where the oil is a very difficult problem. But the response to the oil will follow some kind of pattern. And then, okay, we can use some kind of compressive sensing solution so that, okay, we can reconstruct the original signal. So here is a simulated example. On this part is the water, and here is the oil. It's not an egg, okay, it's some oil for the different response. And then, okay, we mix together, and then we can reconstruct the original signal. So by doing this, okay, we can use a very limited sample to locate where the leakage oil for that. So this one, okay, we try to sell the local oil company, and they say that, okay, they say that, okay, they never leak. So we cannot sell to the oil company for that. Anyway, so the conclusion is that, okay, for this kind of for compressive sensing, the random is good. And for the compressive sensing, the key idea is that, okay, you need to have some kind of sparsity. And this sparsity can be any domain for that. And by exploring this sparsity, we put a random projection. random projection so that we mix these things together. And then we mix them together to a much lower dimension vector. And then by sampling this much lower dimension vector, we can reconstruct the original signal with very high fidelity. And so the key idea is that, okay, we move the burden from the sampling to the computation. And sampling is much more expensive than computation. Computation, you just need a computer or this kind of a CPU. But sampling, ADC, is very expensive. For example, when you buy the digital camera, how much the digital camera cost when this number of pixels is 20 meg? It's probably $2,000. But if you have say, okay, 5 meg digital camera, how much it cost? I think it's less than 100, right? So this is the key idea. Okay, we use this kind of we move the burden from the sampling to the computation. But the challenge is that, okay, everything happened before ADC. So your random projection need to be done in analog domain. This is a very difficult one. And currently, okay, this is a major challenge for this compressive sensing. And currently, the most successful compressive sensing application is this MRI. And this MRI can be easily mixed together. And that one, GE already have some kind of this kind of product by using the compressive sensing for MRI. And finally, I try to sell my book with Professor Husheng Li and Professor Wu Taoyin, and it will be out next year. And okay, finally, I try to talk about my other work in this, my research lab. And because I came from Houston, and in Texas, we have more than 50% of Hispanic people. So I call my research lab Amigo lab. And so that Amigo means a friend in this in Spanish. And currently, we concentrate on the compressive sensing and the game theory, security, and smart grid communication. And for the game theory, we concentrate on this kind of a coalitional game, and we have the different applications like the spectrum sensing, unmanned air vehicle, all these type of topics. And for this security, we try to use this kind of device identification for this using the Bayesian non-parametric. And also, we try to use some kind of trust management, belief network, and Gaussian-based distributed Kalman filter. And we also work on the quick detection and this physical layer security and prime user emulation attack. And for the smart grid, recently it's a very hot topic, and we are working on this kind of force data injection and PHEV optimization and distributed microgrid control and renewable energy. And also, okay, I'm eager to find some kind of possible collaboration here. And finally, thank you very much. Yeah.
Quick questions? So, you think about sparsity? I think it was the channel estimation problem. Yeah. So, can you explain? Is that you're looking at the channel vectors at different time points?
Okay.
What do you mean by joint sparsity?
For joint sparsity means, okay.
I think you also mentioned joint sparsity somewhere else. So.
Yeah. For joint sparsity basically means, okay, these are X matrix for each vector, for each column, times this matrix, F matrix, I will get each column of this M matrix. This is one set of the compressive sensing. And because I have a multiple set, and all these kind of equations have a similar solution, because only on this row, the other is zero. So because we try to explore this kind of structure, and then we can use a joint sparsity solution for that. So this is where the joint sparsity comes from.
Okay.
Please.
Yep.
Is it true that each cognitive radio user sends off like P reports instead of N reports?
Yeah, I think the report will P times N. But what?
You have M's
I mean,
cognitive radio
each
users.
one will have frequency selective filter. So basically, I have P times N, a report. But this P times N might be much smaller than N. And in the simulation, we show that, okay, P times N is about 20%, for the simulation result. Yeah, this is how we define the sampling rate. Yeah.
Yeah, go ahead.
I wanted to know if the lidar technology was something that's being developed now, or if it's actually been used for the anthropology field at all.
Can you repeat your question again? Sorry.
I was curious how old the lidar technology is. Is that something that's being developed right now, or is it something that's been actually used in, like in applications we were talking about, maybe like finding Mayan temples and things like that?
Yeah, for LiDAR system, okay, they are using this one, they try to put into the different application, and LiDAR is already there for a long time. LiDAR system, as I mentioned, for the IC, also for the spectrum, all these are kind of open problem. And you want to increase the accuracy. And also, okay, for this kind of different, you want, on the other hand, okay, you have multi-spectrum, you want to see what is the material there. So all these things are still a kind of open problem. Yeah. And the data rate for that is huge. And by using compressive sensing, we try to reduce the data rate for that. Yeah. Sure. No, we know that. But if I design a kind of random projection purely kind of F matrix, it will be difficult because this F have to satisfy some condition. However, look at this problem. Okay, the matrix R is random projected not only by F but also by channel. And this channel, we don't need to know the information. So basically, okay, we random project twice by F and G. And then, okay, so overall, it's sufficient enough for this one. And F, I will say that, okay, either by some kind of wideband frequency selective filter or by some kind of multiband kind of filter is okay. But F should be implemented in the analog domain.
All right, no more questions. Let's thank the speaker.